Hello everyone and welcome back to the continuation in our series Introduction to the Finite Element Method, in which we are going to basically cover the most topics in the book A First Course in the Finite Element Method by Daryl and Logan. And in this video we're going to be talking basically about 3D stuff. So now we are going to talk about truss elements in 3D space. So we are, of course, basically approaching the end of chapter 3 of that book, and I'm really interested and excited to tell you that it's only going to get better from now on, because later we're going to talk about beams and shells and plates, so it's going to be awesome. Still, today we're going to talk about 3D space and how we can find the transformation matrix, the global stiffness matrix, and use it to solve finite element method problems. For the future, we'll be talking about the inclined energy approaches next time. All right, so sit back, relax, and enjoy the show. Okay, so the first topic we need to cover is transformation in 3D space. The transformation in 3D space is somehow similar to 2D but is expanded, meaning that there is a third extra axis or dimension we should take into consideration. Now, the reference textbook, the book from Daryl and Logan, uses a longer cross-product approach to find the transformation matrix. I think I have another idea, and the idea I have is, well, you have the global x-axis, which has a u displacement in it. You have the global y-axis, which has a v displacement in it. You have the global z-axis, which basically have a displacement of w in it. Now, the idea is, if you know the angle between the x-axis and your local x-axis, then you can take u and just basically cosine it, like multiply by cosine this angle. If you know the angle between the z-axis and your local vector, then you can cosine your w, and so on. So the idea behind this being that we need to find the angles between the global axis and the local x-axis to be able to find the relationship between global and local. In other words, long story short, you have 3 displacements in global, which means you need to switch them into local, so you need the angles. Now, before I continue, you might remember those angles as being called direction angles, having the values of alpha for x, beta for y, and gamma for z. It depends, of course, on what your literature was. At least from Hibbler's book in static, we call them alpha, beta, and gamma. Also, alternatively, the direction angle cosines can be basically the components of the unit vector. What I mean by this is, between point 1 and point 2, there is a 3D vector in space. The unit vector from 2 to 1, basically 1, 2, contains the direction cosines. So there are multiple ways of finding those direction angles and cosines. Okay, so long story short, if you have the angle between x global to x dash and y global to x dash and z global to x local or dash, then all you need to do is to take the global displacements and cosine them to find the local displacement. We also refer to the cosine alpha as cx, cosine beta as cy, and cosine gamma as cz. You can find them also from unit vectors. It's also noteworthy that if you have 2 points, point 1 and point 2, then you can find alpha, cosine alpha, which is your cx, by saying delta x over the length and so on for y and z. Notice that L is Pythagoras of the difference, like x2 minus x1 square plus y2 minus y1 square. The length here is basically Pythagoras, which basically means L equals, delta x square plus delta y square plus delta z square under the square root. Now, please notice that, of course, I'm only talking about u. So what about y, v dash or v local and z and w local? Which means, what about the movement in the local y and local z? Nobody cares, because truss members do not care about the local movements in their local y and z axis, because the only movement that generates forces in a truss member is the movement in the local x axis, which we denote to as u dash. So basically what we see here is a transformation matrix, because look at this. You are saying that u dash equals ucx, ucy, ucz, meaning that your u1 dash and your u2 dash, which means the local movement in the x for point 1 and point 2, will equal, well, cosine of u global, v global, w global. Of course, since we're talking about the movement local 1, you would have u1, v1, w1. And also you would have the cosine x, which means cosine alpha, cosine beta, cosine gamma for u2, v2, w2, which means that the local displacement on the second node is going to be the cosines of the movements at the second node, which means you will fill here with zeros, and that's the reason why you see this as your transformation matrix. Long story short, you can read the transformation matrix as follows: U local on the first node equals cosine U global, cosine V global, cosine W global for node number 1, and then nothing with regard to node number 2 because U1 is well based on node 1. When you want to find U local at node number 2, you don't need anything global from node number 1, but you need, of course, everything global from node number 2. So you say Cx U2 plus Cy V2 plus Cz W2. I hope this makes sense. Okay, so this is the transformation matrix we have, which basically means that now I am able to solve. How do I solve? Well, this is something that does not change. The global element stiffness matrix. We are talking about the global stiffness matrix of an element because those are going to be used to find the structural K capital global stiffness matrix by means of summing those up. So the element global stiffness matrix is, well, as you know, transformation transpose, local transformation. In other words, it's this big thing. This is your local stiffness matrix, AE over L, 1 minus 1 minus 1, 1. This gets pre-multiplied by the transpose and post-multiplied by the transformation matrix. Of course, the book now gives you one full shortcut for this, which gives you K, which is the element global stiffness matrix, which basically gives you this. Now, what is this big matrix? This big matrix is basically the solution of this entire calculation. I am not a fan of it, to be honest. I like to take the mathematics approach of saying T transpose KT. Why is that? Because I need to always keep the K local available for me, because sometimes I might have the forces in local, sometimes I might have the displacement in local, and I want to find the forces in local, which equals the stiffness local multiplied by D local. So personally, I don't calculate this. Personally, I calculate the transformation matrix and calculate the local stiffness matrix, and then let MATLAB or any mathematics software calculate the global stiffness matrix for me. And you will see me doing this in the example. So this is an example taken out of the book, of the reference, and it basically gives you a truss, a very small truss, mind you. It gives you basically a truss made out of 3 members. You can see the following. You can see there is node number 1, and element number 1 connects 1 with 2. Element number 2 connects 1 with 3, and element number 3 connects 1 with 4. And now he wants you to basically calculate the following for the truss. He gives you the elastic modulus, he gives you the force 1000 at the z-axis at point 1, going down, and he basically tells you that this is a pin, so no movement. This is a pin, so no movement. This is also a pin, no movement. And this is a roller, basically a wall, that prevents the movement in the Y. So you know the pin, the joint here cannot penetrate back or forth on the wall. Now, here is the thing about this support. This support is a roller faced or resting on the wall behind it. And for a BSc student, that's fair enough. For him, the assumption of a roller means that if you have a roller on the wall, it can carry both tension and compression, because you're assuming that the roller is not going to be detached from the wall. Even if you have this type of roller, you have studied this in statics or whatever, if you have this type of roller and you apply, for example, a force going up, then you assume that the two reactions are going to go down. Although the roller, so your assumption here is that the roller doesn't get detached. And this basically means that our drawing for the roller was actually a lie. The truth to be said here is that I should draw the roller like this, like this, with the ball running like this. That's a true roller, because this roller will actually be able to carry both tension and compression, but nobody cares because you know those limitations. This is for BSc. In MSc, you might really deal with this as a smooth surface. This means that the reaction is active if your point wants to go into the wall, which means your reaction becomes active and resists. and it becomes inactive if your point moves away, so there is no reaction at that point. So this becomes a kind of strange problem where you have to determine if point number one is this one at the wall, if point number one wants to move into the wall or out of the wall. And a cool way of doing this is, at least for this is now a simplistic way of dealing with it, is to assume at point one that there is no support, and if point one wants to go in the positive y, then recalculate assuming a support, because the support would resist. However, if you assume at point one no support and realize point one wants to go away from the wall, then your assumption is correct and you don't need to recalculate. This is really cool, but this is very simplistic. Sometimes you have multiple walls like this and it becomes an iterative analysis. Of course, feel free to think about this at home. For me, if I see a roller, then I assume it can carry both tension and compression on the roller. Because remember, our course here is an introduction to the finite element method. Later, I would start a finite element method deep dive course in which we're going to be talking about nonlinear analysis and all this kind of stuff of Newton-Raphson iterations and so on. But for now, we are doing an introduction, so I think that's fair enough. All right, now what does he want from me? He wants to find the movements or the displacements. He wants you to analyze the truss. For me, analysis means find the displacements of all points, and if you want, you can find the forces or stresses inside those members. So, okay, let's continue now. Of course, here I have my structure on the side, and this is a 3D structure. I'm going to use personally this. The reference book doesn't use this. The reference book uses the quick method of finding one simple matrix. I don't. I like to use the step-by-step matrix, because why not? So, okay, let's dive into it. Starting with this, for element 1, which goes from point number 1 to point number 2. This is the element in red. You need to, of course, find the codirection cosines. So point 1 is this. Of course, the coordinates are given. You can see them here. And point 2 is this. And we know that the vector is basically point 2 minus point 1. In other words, delta x can be calculated, delta y, delta z. You can find the length by Pythagoras, and then find cx and cy and cz by basically finding the cosine of alpha, which is delta x over L. Of course, I'm relying on your knowledge in physics and basic geometry to infer those points. So basically, you can find them by saying delta x over L and so on. Well, that's that. Of course, I can find the local stiffness matrix by saying AE over L with 1 minus 1 minus 1, 1. And of course, now I need the transformation matrix, which looks kind of like this. This is CX, this is CY, and that's CZ. Those 3 zeros are natural because remember, the local displacement of point number 1 in the X doesn't feel anything related to U2, V2, and W2. There is no relationship between them, but there is a relationship between U1, V1, and W1, and that's why you see values here and you see nothing here. This 0 value is just because this bar is horizontal. So indeed, the horizontal doesn't have any cosine in Z, meaning that if you move this bar 1, 2, if you move it locally in the X or whatever, like 500 units in the X, then the Z doesn't feel anything. Also, if you move it in the Z, the X doesn't feel anything. It's kind of cool. Continuing with this, of course, we have our second point or bar. In this case, I have 0, 0, 0, and then Cx, Cy, Cz. So that's my transformation matrix. Of course, this becomes a little bit prohibitive if you want to calculate this by hand. So I'm using MATLAB to do that for me. I just define now, and I hope that you know MATLAB. Or there's also an Octave, another program called Octave. Both of them are really good for numerical analysis. So I define my stiffness matrix, I define my transformation matrix, and I calculate, and I get this for the local stiffness matrix, this for the transformations matrix, and this for the for the element global stiffness matrix. I will talk about this later when I start assembling my global stiffness matrix, because as our dear member Donald Khania says, well, whenever you see stiffness matrices, you think about assembling. We continue now. That's for element number 2. And for element number 2, I did everything automatically here. You can actually type this in MATLAB and get the perfect answer. So I'm giving the elastic modulus, the area, the starting point, the ending point. I'm asking you to find the vector, the length of the vector, the local stiffness matrix, and then transformation matrix, global stiffness matrix. This is just step by step. Rinse and repeat for element number 3, and we have our element stiffness matrix. And of course now the fun starts, because now we want to assemble our global stiffness matrix. Now please notice that this lecture is a continuation of a full series that I'm going to link right now in the top right. So as we are repeating examples over and over and over again, I'm assuming that we are really like getting better at this. So I'm now basically filling blocks instead of circles, because why not? I think we should be getting better at this. So now let me remind you, this is the global stiffness matrix, right? And how many points you have? You have 4 points in the structure. You have node number 1, 2, 3, and 4. Now each node can move in 3 directions. It can move in X, it can move in Y, and it can move in Z, which means each block is a 3 by 3 block. Okay, now how do we think about this? Node number 1 with node number 1. I'm talking about the block now. In the last lecture, which I will link above here, we talked about U1 with U1 and V1 and so on. Now, because we're getting better at this, I'm going to just say node 1 with all its movements, U, V, and W, with node 1 with all its movements, U, V, and W. How can I find those things? Well, I need to see the symbols, or I need to see the elements that have node 1 in them. Now, lucky for me, all of the elements have node number 1 in them. For example, this is from node number 1 to 2, which means that the first block here is node number 1 with node number 1. Because if you split this into 4 quadrants, this would be node 1, this would be node 2, this would be node 1 in the rows and node 2 in the rows, which means that node 1 with node 1 is this quadrant. Similarly, this quadrant and this quadrant. So what remains is you should add them together. Adding them together gives you this. Of course, what about the values here? I haven't filled them because symmetry, meaning that if this is negative 3.6, then this is negative 3.6 as well. We go on to the next block. This block gives you in the column node number 2 and in the row node number 1. Of course, the only element that deals with 1 and 2 is element number 1. It starts from 1 to 2, so that's node number 1, and that's node number 2 in the columns, as well as for the rows. That's node number 1, that's node number 2, that's the block I want, and you can see me writing this indeed here. We continue and go to the next block. This is block of node number 2 with node number 2. You see where this is going, right? I'm going to keep rinsing and repeating. Of course, the only element that has node 2 in it is this element, and node 2 with node 2 is this quadrant, so you can see filling the values. We go on, and you see the matrix is now getting bigger and bigger. We go on to column node number 3 and row node number 1. The element that has 3 and 1 in it is this element, I guess. No, sorry, this element number 2. So of course that's the quadrant I want, because this quadrant connects node 3 with node 1. So you can see the values being shipped here. We go on. You can see that this here is node 3 with node 2, and there is no element that connects them. You can even see it here. That's node 3, that's node 2. There is no direct connection between the two of them, so none of those stiffness matrices has a element with 2 and 3, so you can see me filling zeros here. We continue, of course, to the next point, and you have here node 3 with node 3 with itself, and of course this block is node 3 with node 3. Then of course you have the final column. You have here node 4 in the column with node 1, and now I'm trying to be a little bit abstract. The only element that contains 1 and 4 is basically element number 3, and you can see since element number 3 goes from 1 to 4, this means that this is node 1 and this is node 4. Furthermore, this is node 1 and that's node 4, so this entire quadrant gets here. Now you can start expecting, I have 1 with 4. Of course, I'm going to say now 4 with 2 and 4 with 3. I'm predicting 4 with 2 is going to be zeros and 4 with 3 is going to be zeros because there is no connection between them. And indeed, you can see here that indeed you have zeros everywhere. Finally, you have 4 with 4. So I'm expecting this quadrant to be taken. Let's take a look. And indeed it is. So now I have my global stiffness matrix. How can I start solving? Well, I need to apply my boundary conditions. What are the things I know? At point number 1, you have U, V, and W. You know that V cannot move, so it's 0, because there is a ruler. What about the other points? The other points, 2, 4, and 3. Those points cannot move anywhere. So for example, you have U2 and V2 and W2, all of them equal 0. You have U3, V3, and W3, all of them equal 0. You have U4, V4, and so on. So you get the idea. The consequence of this is, if you apply your global equation, your global stiffness matrix, the second row gets eliminated, as well as all those rows. The only rows that still survive, and columns, sorry, not rows, columns. The only columns that still survive are the column here, which is the column of node number 1 in X, and the column here, which is node number 1 in Z. Why do those survive, as well as their corresponding rows? They survive because, you see, for all of those you have zeros, but you don't have 0 for U1, you don't have a 0 for U1, you don't have it, and you don't have a 0 for W1, so you cannot simply eliminate them. This makes your problem much simpler, because now you can just solve, and that's it. Because now, you see, 8.96, 2.4, 4.39, and 2.4, because symmetry. So take a look here, it's 9,000, not 2.4. You see, of course, there is a slight difference between me and the book Dariel and Logan. The reason why, because I was a little bit more accurate than him. I was using MATLAB, which of course gives you a higher accuracy. In the book, they are just using a simplified accuracy. For example, in MATLAB, you use 0.333 until 15 digits, but in the book, they only were using 0.33, 2 digits. So there was some approximation involved. But nevertheless, you can see the values just fine. And what are those? Well, those are the global force. This is the global force vector. Okay, what is the global force vector? The global force vector is, well, the forces at element number 1, at node number 1, sorry, the forces node number 2, the forces node number 3, and the forces node number 4. Of course, after you eliminate everything here, what will survive? What will survive is the force in X at node number 1 and the force in Z at node number 1. And if you take a look here, the force in X at node number 1 is indeed 0, and the force in Z at node number 1 is 1,000, but wait, it's going down. From that, you can find the displacement. Please notice that now you can solve everything. You can find the reactions, and I want you to try this. And of course, I'm not doing that because I've explained this in multiple videos before. I will link some of them here above. And then from those, you can find basically the stresses using this cool equation, which is a shorter way of finding the stress. I have explained it differently, in which I want to find the local force and then basically divide by the area. This is a shorter version of that. So you can find those stresses, and well, that's basically everything. Now, I know what you're thinking. You might think, whoa, that's a shorter lecture than usual. The reason why is because we are not really adding new concepts here. We are just expanding on concepts you already have. So we are dealing with 2D, and now we are dealing with 3D. And you can see that it's just almost the same. And this would the same feeling you will have in the beams and the frames and the plates. So this feeling, to be honest, is really kind of good. If you have the feeling that, hey, I think I've seen this before, I'm only learning some new aspects in this lecture, that's very good, because exactly this is what will happen during the lecture series. Because remember, this is like a quick lecture series in the finite element method. So I'm going to deal with it, of course, step by step. And there will be some repetitions, like you will have to assemble the global stiffness matrix every single time. But you can see me getting a little bit faster in this. Like you can see me not really going into like painstaking detail as of how we've done it. We're just like block by block now. Like last time I was doing it element by element, and now we're doing it block by block. So I hope that you enjoy this kind of presentation style. Anyway, for the next video, we're going to wrap up chapter 3, because we're going to introduce something called inclined reactions, meaning that you have reactions that are not aligned with the global AZ and X and so on, but rather have their own local system. We're going to deal with that, and we're going to cover something called the energy methods for the derivation of our truss element AE over L, 1 minus 1 minus 1, 1, and so on. So stay tuned for more videos. because there's going to be a lot of them. We're going to keep continuing doing this first course in the finite element method book on a weekly basis. That's everything I wanted to talk about in this video, but before I finish, I want to give a huge CEE-sized shout out to our dear channel members whose names are going to be shown on the screen. Of course, I want to thank every single one of them for considering contributing to the CEE channel. Their contribution helps us produce better and more video tutorials, and for that I'm really thankful. With that being said, I hope that you enjoyed the video and that it was beneficial for you. If you have enjoyed the video, then please like, share, comment and subscribe, especially subscribing, because it helps increase the reach of my channel. As per usual, this is the Civil Engineering Essentials channel, and we'll catch you in the next video.